today, exceptionally, we'll have just one lecture entitled Quantum Crystallography, Past, Present and Future, which will be delivered by Dylan Jayatilaka from the University of Western Australia at Perth. Dylan completed his bachelor degree in science with honors in chemical physics at the University of Western Australia. Then he got a PhD at Cambridge University in the United Kingdom in theoretical chemistry under supervision of Professor Nicholas Handy. Next, he became a National Research Council USA Research Fellow at the NASA Ames Research Center, and then Australian Research Council Research Fellow and Senior Fellow. And in 2001 was appointed a position at the University of Western Australia. Dylan was a visiting professor at the École Nationale Supérieure in Paris, at the University of Henri Poincaré, and also at the University of Bremen in Germany and University of Bern, and also visited us 2 times in Warsaw. Dylan is a quantum chemist and with interest in crystallography. Actually, in my opinion, he's the practical founder of the whole field of quantum crystallography. He, together with Daniel Greenwood, his first PhD student, presented the first experimentally determined wave function constrained to reproduce the X-ray diffraction experiment. Together with Birger Dietrich, developed Hirschfeld atom refinement, and in a series of papers demonstrated the power of this method, especially as far as hydrogen atom positions are concerned. Together with Piero Macchi, Dylan chaired the first school in quantum crystallography at the RICE. And Dylan worked for a long time together with Professor Mark Spackman, developing probably the most popular piece of crystallographic software, which is Crystal Explorer. And of course, also developed a new method for calculating molecular interaction energies. Dylan got almost 18,000 of citations with H indexes 50, and today will present his lecture. So Dylan, the screen is yours.
Okay. Thank you very much for that really very complete introduction. And here's my talk. So this is a picture of where I still work for a few more weeks. And because I'm in Australia, we are obliged to acknowledge the traditional owners of the land, Ngala Kadich, Nungamut, Koyen Karap, Nija Buddha. That's the Noongar language from the people who have been living here for 60,000 years. Okay, this lecture is a slightly expanded version of the keynote lecture which I gave in Prague. I wasn't that happy with it, both from content and also technical problems. So hopefully, I think we won't have technical problems this time. But I'm still a bit incomplete in this presentation, so I'm sorry about that. So here is the rough outline of the talk: past, present, future. I want to say a little bit about crystallography and IUCR, and especially focusing on the topic, what is quantum crystallography? So I hope I can introduce that idea in a relatively simple way for people to understand. And especially trying to link quantum crystallography to quantum chemistry and linking it to the history of crystallography as well. Okay, I will say a little bit about what's happening in the present time. Unfortunately, not too much, because there's so much work going on at the moment. I don't think, well, it's just hard to summarize. A lot of the problem is from our chairman, who's just generating huge amounts of work. But I will try and summarize that properly. And it's also a pleasure to be asked to give this talk. I've had a long association with the Warsaw group, a lot of very talented ladies who have worked with have come to Australia as well. And that has been really fun. Okay, so these are the things I'm going to talk about in the present. In the future, I actually ran out of things that I was going to talk about here. So I just put down a series of points. Perhaps that's something that we can talk about in the question time. Okay. All right. So crystallography and IUCR. So this is Peter Ewald. He was one of the main founders of the IUCR organization. It had a bit of a difficult beginning, Ewald and Evans. And I thought it would be good to review a little bit about what he thought crystallography is. And it's interesting to do that review, because actually many of the things he said are really pretty relevant today. Essentially, what Peter Ewald was considered himself in the end to be a physicist, but in fact the International Union of Crystallography started off in physics, but he argued pretty strongly that crystallography should be its own field, mainly because of its extremely interdisciplinary nature. He was really very strong that crystallography should have a lot of overlap with chemistry. And of course, it has a lot of interaction with biology. Even today, now, even though we have some work on biological crystals, and now even systems which are perhaps not crystalline, but I still think that they qualify under the definition of what Peter Ewald intended crystallography to be. And I will show you that in a second. Because if we go to what Ewald wrote, this is his paper from 1944 in Nature, before the union existed. And this paper is essentially, it's a beautiful piece of work, actually, if you read it, arguing that what crystallography should be and why it should be distinct from physics and other things like that. And if you read it, it has really a lot of relevance today. I want to read just the last few paragraphs. I think it's so important, it's worth actually reading it out to you, because it will kind of explain where we're going. So at the end of this plea to start the IUCR, and it eventually did happen, he wrote this. He said, "A word should be said about the use of the term crystallography. American and British societies referred to earlier have avoided this term in their names and have stressed instead the method of observation that they wish to promote. The main reason for this may have been the fact that X-ray and electron diffraction methods are being applied also to substances which are not crystals, such as fibers, proteins, colloids, even liquids, and the molecules in gases." So we're talking about gas phase electron diffraction here. So even in those days, there was some concern about whether crystallography was actually being applied to what crystals were. But let me continue. While the titles chosen give a clear indication of the main present activity of the respective societies, I would suggest that they imply a restriction which ultimately be either abandoned or prove undesirable. For any particular method, after having been applied for some time, tends either to become a routine method of observation and as such of minor interest, or continually to be merged with other methods supplementing it from fresh sites. In the case of X-raying the method, this latter happened first when W.L. Bragg drew up a list of atomic radii. Later, optical and magnetic observations and the principles of atomic physics and of crystal chemistry, which were being established, were added to the armory, supplementing the diffraction method. They were added to diffraction. For how long will it be true that the main interest of the two societies lies in the diffraction and not in the supplementary methods, such as, you see what he's getting at? Are not many of their members interested mainly in applying the results gained by diffraction methods to the elucidation of chemical, mechanical, and physical properties? Is it not one of the main aims of these societies to link X-ray diffraction with whatever chemical or physical methods seem to be promising to supplement it? The present circumscription of the society's activities is decidedly too narrow. So, and finally, he continues, the crystallography in its original meaning does not, it is true, include the entire field of application of diffraction methods, but it does cover the main field even then. Leptology, which Rinne coined for fine structure, would be preferable to crystallography, but the word has not been generally introduced, and this might not be a good occasion to plead for it. Unless something new is adopted, however, crystallography will have to be used in a wider sense than originally intended. So you see what he's saying? Crystallography was always a bit of a problem, and it always had to encompass more than just the notion of a perfect crystal. So as to cover substances which for some purposes may be regarded as inferior forms of crystal. In them, the arrangement of the atoms or molecules, while showing some kind of regularity, departs further from the perfect three-dimensional symmetry, homogeneity, and periodicity than in the actual pieces of quartz to which the name of crystal was originally applied. The remaining regularity may, however, suit to make profitable a close connection of substances regarded from this aspect and of the old-time crystals. And it is this enlarged field which the term crystallography should be understood to cover. Now, before this, Ewald is arguing for the construction of an international tables because there were so many errors in the space groups, tables which included structure factors, and these tables, as you know, did get made. He also suggested the construction of archives, and these archives have also been made. And there's a few other suggestions there, which he argued that crystallography needed to have. Okay, so in summary, crystallography is that field of study concerned with solid materials whose atoms have some kind of regularity, not perfect regularity, but the regularity is normally spatial. Okay. And of course, just to complete that, a field, because we're talking here about what is quantum crystallography. So first, let's concentrate on crystallography. A scientific field is defined by a coherent body of knowledge pertaining to the material studied, as well as the methods and techniques used to obtain that knowledge, theoretical, experimental. So a field of study is concerning things that are being investigated, a subject or an object in terms of type of material, as well as the methods together. So it's not just the methods itself. I think that's a fair call, methods and techniques. It's also the materials. But just remember that crystallography was a rather broad thing. Okay, so quantum crystallography. Okay, so let's see what the original definition was. Quantum crystallography, and this was the definition of Masa Huang and the Nobel laureate Kahler. And there's a nice review here by my colleagues, Grabowski, Giannoni, and Berge. The original definition from 1995 was quantum crystallography concerns the combination of crystallographic data with quantum mechanical techniques in such a way that it should be possible to obtain enhanced information of enhanced value. So it's interesting. It's basically a technique of combining data and quantum mechanical methods. Okay. Here's the viewpoint from the dichotomy between theory and experiment. This is from the review that I mentioned from Grabowski. And you can see here they tease out that definition in two ways. On the top way, you can see they're combining quantum chemistry and crystallography, but on here they have quantum chemistry on top. And the idea here is to get some kind of experimentally derived wave function. So when I first gave this talk, actually in the Missourian Lakes at the Sagamore meeting organized there, that was a very nice meeting, but it was quite controversial. And in those days, I said a lot of controversial things, and I was punished for that. Anyway, because you can't really say experimental wave functions, because I was always taught a wave function is unobservable and things like that. So that's a controversial thing. But the idea is that you get, as it says here, an experimental wave function, which is an improved approximation to the true wave function if you can use crystallography information to incorporate that into the quantum chemistry. So the key thing is the wave function, which is being improved by experiment. Okay, the other way to think about it is in the opposite sense. It's a second aspect is to integrate the wave function into crystal structure determination to improve the dynamic charge density. So here, the intention is not to get the wave function, but to get an improved property out of your analysis. And it's some kind of improved observable. But rather than being a direct measurement of the thing, you are actually taking the model to be the wave function itself. Now, this is not such a strange idea as you might think of. In spectroscopy, they have things called model Hamiltonians, where rather than using the actual Hamiltonian, they just use up they postulate a model Hamiltonian with parameters. You may have heard of the Ising model, for instance, in physics to describe magnetism. And these model Hamiltonians are sort of fitted to the spectra in observed experiments. Well, the idea is very similar here, at least in the top sense. Instead of a model Hamiltonian, you have a model wave function. So somehow it's a partner to that kind of idea. Okay, and in the second sense, we're concentrating more on the property. The dichotomy is you have theory and experiment, theory improving experiment, or experiment being enhanced by the incorporation of theory. So there's these two things, theory and experiment. Okay, let's keep going. I want to read to you this dichotomy because I want to deconstruct it a little bit. And a long time ago, I found this quote, this very nice exchange between Einstein and Heisenberg in this book by Use. Let me read it out to you. So here's the conversation between Heisenberg and Einstein. So Heisenberg comes up to Einstein and he goes, "Hey, so you're saying that one cannot observe the orbits of electrons in an atom, right?" You know, that's Heisenberg uncertainty principle. And then Einstein says, "Hey, seriously, you can't believe that a physical theory be based only on observable quantities?" Heisenberg, astounded, "I thought that exactly this idea was essential for your theory of relativity." You know, his theory of relativity being based on the observation of constant speed of light, at least special relativity. Okay, now Einstein says, perhaps I used this kind of philosophy, but it is nonsense nevertheless. It may be of heuristic value to recall that of what one really observes, but from a principal point of view, it's quite wrong to insist on founding a theory on observable quantities alone. It's quite wrong. Listen to what he's saying. It's quite wrong to found a theory on observable quantities alone. So he's really not one of these logical positivists, Einstein. In reality, just the opposite is true. Only theory decides about what can be observed. My emphasis. On the entire long path from a process up to our conscious perception, we need to know how nature is working, even before claiming that we have observed anything at all. He's a very clever dude, Einstein. Okay, so that's just to say that the idea of experiment being separate from theory is a bit of a strange thing. All right, let's come back to quantum crystallography, because we're mixing theory and experiment here, trying to get experimental wave functions. So Cyrilson proposed this definition in 2018. Quantum crystallography is a research area, and by the way, he's also one of the main founders of this field, I would say. Quantum crystallography is a research area exploiting the fact that parameters of a quantum mechanically valid electronic model of a crystal can be derived from accurately modeled or measured set of X-ray coherent diffraction structure factors. Seems pretty good. Now, Mackey suggests that the restriction to X-ray diffraction experiments in the bottom here is really a bit limiting. I looked at his article from 2020. He didn't seem to have a clear definition, but I induce from what he was writing that what he intended that was that rather than X-ray coherent diffraction structure factors, we should perhaps replace here using crystallographic methods. And as I said before, these can be either experimental or theory, because a field of crystallography involves both the study of the materials and the methods together. I think that's pretty clear. And also that was intended, I think, by Ewald. Okay. We asserted before that these methods could be theoretical or experimental. And of course, theoretical quantum mechanical methods are by definition quantum mechanically valid. We'll come back to this notion of valid in a second. Okay, now I want to propose an alternative. I've been thinking about this for a while. Non-dichotomous viewpoint. I feel that definition still doesn't quite capture the original definition and the close combination of experiment and theory inherent in the definition of Kahler and co-workers, Massa. So I would say quantum chemistry is a research area which constructs or reconstructs quantum mechanically valid models of a material, crystallographic material, with some degree of regularity in its structure, that's crystallography, using a protocol which makes use of experimental crystallographic information. Note here I include experimental here. So the reason for doing that is so that this definition explicitly excludes purely theoretical calculations, because I feel that quantum crystallography should really be, this is probably a very minor point, but I think it should be an experimental field, supplemented by theory, of course, but I think the raw thing is experimental. Now, we need to concentrate a little bit on this word valid. The term valid might be interpreted liberally. I think it should be interpreted liberally to incorporate, for instance, multiple models, because they, after all, are based on atomic quantum mechanical models. They make use of atomic orbitals in here. So there's some kind of quantum mechanical information going in there. That kind of information, I think, is valid in some sense. And it's really a matter of taste how much you decide what valid is. For example, even the models we use do not satisfy cusp conditions. And everyone knows that there is a cusp condition between electrons and the electron and nucleus. None of our wave functions satisfy that condition, even though the electron density might be positive. So we need to be a little bit forgiving, I think, on the valid word. Now, I also use the word constructs or reconstructs. So reconstruction is a distinct notion from experimental determination. Reconstruction is not experimental determination because, in my view, when you reconstruct something, the distinction between experiment and theory vanishes. That's not really, it's the objective of reconstruction is not really measurement, but really trying to get the best possible view of an underlying reality. So it's a kind of positing that there is an underlying reality there. And in that case, reconstruction applies to inherently complex situations where there's an imperfect experimental information available. And it's closer in the concept, it's closer to the concept of learning than measurement. You're sort of reconstructing stuff. It's not really very preferable. If you can, you should be doing proper experiments, in my view. The fact is that when you come to very difficult situations, you can't do perfect experiments and you have to get into this regime. So reconstruction generally applies to a selection of a model from a family of models where there are more parameters than data. Okay, so I hope to explain that to you in more detail. If you're interested, you can look at this paper by Leone 2019. I think it's really a very, very detailed view of the experimental situation at the moment. This paper covers, with examples from the biological sciences, a more iterative view of measurement and theory, which is more in keeping with Einstein's idea that experiment builds from theory and theory builds from experiment, rather than this dichotomous view of here are the theoreticians and here are the experimentalists and we fight together. I think that's a useful view. We should always be trying to go for that, but actually that's not how it works in reality. It works like this. Okay, now let's move to quantum chemistry and quantum crystallography, the relationship between these two things, because they are quite close. The underlying physical laws necessary for the mathematical theory of the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. So this is the famous quote from Dirac, which is the basis of quantum chemistry. Okay. Here are the two Nobel laureates who got the prize in 1998, Walter Kohn and John Popel, for theoretical chemistry, computational chemistry, method development, which was and is now some of the backbone of the simulations of properties that we are all mainly take for granted in the form of quantum chemistry programs. Particularly interesting for this talk, Popel was mainly concerned with wave function development methods and systematization and benchmarking, and Walter Kohn's contribution concerned the development of density functional theory, which is the theory of quantum mechanics that does not need any wave function. It doesn't need any wave function. A quantum mechanical theory that doesn't need any wave function, but in fact it only requires the particle density, which, by the way, is a measurable quantity. So already at the stage of 1998 or before, Walter Kohn had shown, according to his own theorem, that the wave function is an experimentally determined quantity because it depends on an observable that can be determined from it. Of course, no one actually thought of doing that. They were more thinking that they could use this electron density to make practical and accurate models, which certainly happened. Okay, for electronic systems, as I say, this means that instead of particle density, we're generally concerned with electronic systems, but it doesn't have to be electronic systems. We can also use density functional theory for nuclear systems. It's a little bit more rare. We only need the electron density, a 3-dimensional function, and not the wave function, which is a 4n-dimensional wave function, depending on the 3 XYZ coordinates and the spin coordinates of the electrons, where n is the number of electrons. So obviously the electron density is quite a lot more simple, and already in that way you can get some simplifications. You can see that's a massive simplification already. So Cohn's idea. Cohn's idea was basically, okay, the wave function is okay, but once you get to big systems, it becomes meaningless. And in fact, he did a calculation and showed that for a system with more than 1,000 electrons, to record a wave function for that kind of a system would require more than the number of atoms in the observable universe. Because of the dimensionality of the system and the degree of complexity of that wave function. So yes, Cohn really says in his Nobel lecture that the wave function is meaningless. So I don't know if he ever talked to Stephen Hawking, who wants to posit the wave function for the entire universe already for 1,000 electrons, according to Walter Cohn. That's a meaningless statement. Funny enough, though, the most popular and extensively used version of the density functional theory does involve a wave function, and that is called the Cohn-Sham wave function, which we'll talk about a little bit in a second. So let's come back to what Walter Cohn did. It's started with the Hohenberg-Cohn theorem. By the way, speakers, can you tell me how much time I've got? Oh, yes, I've got the clock here. Oh, dear. I'm going very slow. I'm sorry. Anyway, here's Hohenberg and Cohn, and they have proved a theorem saying that the electron density is sufficient to derive the potential and then the wave function, which is a kind of repository of all the valid quantum mechanical information. Now, the proof of the Hohenberg-Cohn theorem is very simple. You can look it up here. It's actually done in 4 lines. And it shows that the electronic energy of the quantum mechanical system depends only on a unique functional of the electron density. But the problem is, no one knows what this functional is. So that's a bit of a problem. There's no systematic way to get that functional. Besides, it was very difficult to approximate the kinetic energy using only the electron density. So as I said before, Cohn and Sham came up with a different scheme. And instead of using the electron density, they used the single determinant wave function, which had the same electron density as the exact wave function, a kind of doppelganger wave function. And using this single determinant wave function, they could approximate the kinetic energy and make good approximate energy functionals for the density. So this is the version of DFT, which uses a simple wave function that's actually used to do all the practical calculations, when it produces really very, very good results for simple systems anyway. And actually, you can show that as the number of electrons goes to infinity, density functional theory essentially becomes exact. But no one knows what the functional is that would give you this energy. Okay, let's go quickly now. The quantum chemistry and quantum crystallography, the earliest quantum crystallography. Here's a paper by James, Waller, and Hartree. So people will know Waller from the Debye-Waller factors, or the atomic displacement parameters in X-ray diffraction. James, of course, I don't know if the young people would know, but he was very important still in X-ray crystallography. And of course, Hartree is the guy who was involved in the Hartree-Fock wave function. Actually, he didn't do the Fock part of it, and he was beaten to publication by Fock, unfortunately. So, but in this paper, what they did was an investigation into the existence of zero-point energy in rock salt lattice by X-ray diffraction methods. And And this was done in 1927, so really at the genesis of quantum theory, really, and using computers. So they were really very, very far ahead, and they did things very quickly. This, I think, is one of the first concrete works on quantum crystallography. Here you can see he calculated the distribution, the radial distribution of charge in Na plus and Cl minus. And what they did is, using these atomic densities, which were derived from quantum mechanical wave functions, they could simulate the structure factors from rock salt. And here you see the curves which match the observed measurements, the little dots here. And this agreement level only happens if you use the charged ions and not the neutrals. So at this stage, the quantum crystallography was used to prove beyond doubt that the crystals were made with ions. I note here that Piero Macchi, in his very interesting article here, argues that the origins of QCR go back even to de Broglie. It's worth reading that paper as well. It's very interesting. Okay, so quantum crystallography was really almost synonymous with quantum theory. Okay, let's get closer to the crux of the matter here in quantum crystallography. Can a wave function be measured? What is a measurement anyway? So here's a cartoon that I used at this Sagamore meeting in the Masurian lakes there up in Poland back in the day, which got me into a lot of trouble. But I just wanted to explain to myself what measurement is. And I don't really like or understand this idea that a measurement is something that you get from a wave function by doing psi star operator psi on an operator. That's gobbledygook to me. This is what a measurement is to me. This guy's measuring a pencil, and he's looking at the pencil and comparing it to something. He first imagines the experiment, how he's going to do it. So that's Einstein's thinking about the theory beforehand. Then he actually goes and does the experiment, and then he gets the result that the length of the pencil is 42. Of course, there's an error here because he's not looking straight down. There's some kind of parallax error. So he can even correct his own model by taking into account parallax, you see. So theory is involved in the measurement. But the key thing is you have a model that you've conceived of, and then you get the length out like that. So can a wave function be measured? Sure, it must be roughly the same procedure, right? So what is the procedure? We make a model for what the wave function is. We imagine an experiment to determine the parameters in this wave function, and we do the experiment. And then we fit what you see to the model you thought of. So here we have the guy imagining an experiment, imagining a particular kind of wave function. He goes, cool, I think I can do that. He goes and looks at the dial, he does the measurement, and then after some mathematical analysis, he comes out with the wave function psi equals 42x. So that's the idea that we have. Let's see how it can be carried out with the X-ray experiment. Remember, the X-ray experiment shoots an X-ray into a periodic system, perfectly imperfect, and you get the scattered X-rays. And in the first Born approximation, the intensity of the scattered X-ray is proportional to the Fourier transform, the square of the Fourier transform of the electron density in the unit cell. So it's the square of the magnitude of the structure factor, Fk. And the K scattering vector is the difference between the incident and reflected X-ray. This was back in the day when we have point detectors. Nowadays then there was a whole time where we had CCDs, and now we're in the realm of multiple point detectors all on a little computer chip, and even energy dispersive. So that's really fantastic. Okay, so that's the measurement that the guy has conceived of. in his head. And now he thinks, okay, I better have a model for the wave function. So the wave function that we're doing is a molecule-based procrystal. So the wave function here is a product of wave functions over the unit cell. And in the first case, we may take them to be single determinants because they are the simplest kind of wave function that includes the anti-symmetry of electrons, which is important. Okay, so how do we get this experimental wave function in reality? Well, there's two cases. The first case is when we have more data than parameters. This is easy. So the parameters that we're talking about here might be the ones that you're usually thinking about, atomic positions and ADPs for the X-ray experiment. But of course, in a different experiment, there may be different parameters. The key thing is you have more data than parameters. So we just use the least squares method. We choose a wave function where the electronic parameters are determined by minimizing the energy. So we have a variational one and a variational wave function. And the other parameters like atomic positions can be determined by least squares. So we do the experiment and then we minimize the least squares error between the predicted and observed data. So the only trick in this is figuring out how the experimental data, well, there's two tricks. You have to figure out how the data can be calculated from the wave function. In this case, how can we calculate the electron density in the unit cell from the wave function? And there is a more tricky business where we have to break the wave function electron density into atoms because we have to thermally smear each of those atoms as they move. Now, the beauty of the X-ray experiment is even though the crystal isn't perfect, each unit cell is sort of a near copy of each other one, and we can use atomic displacement parameters to model the vibration. So this kind of idea is not so different to what's done in electron diffraction imaging with cells, these accurate images. What they do there is instead of unit cells being all the same, they have crystals in different orientations and they organize them into classes, and the repetition there allows them to extract information from the cells. But here the repetition is naturally done through the near translational symmetry of the crystal. Okay, so, and we mustn't forget to recalculate the wave function every time something changes. For example, when the atomic positions change, the wave function changes, so we have to recalculate it. Okay, here is the chi-squared. I just put it down here. You will know it's the difference between the calculated and observed structure factors divided by the number of reflections minus the number of parameters. Actually, the correct term for this is the goodness of fit squared. I was a bit lazy, and this is a terrible mistake. It really should have been called goodness of fit squared. I think in the future we will use that correct terminology. So that's the least squares error. The tricky thing is to calculate the model structure factors. And the formula isn't very different from what you're used to. There's an atomic form factor, which is summed over all the atoms in the unit cell with translations and rotations. And the only trick is that in this case, the thermally smeared structure factor, which is here as a product of the temperature factor, the Biwaller factor times the static electron density, is aspherical. So this thing is aspherical. And all of these things, scale factor, atomic positions, and ADPs are refined. And the number of these quantities here is the number of parameters in the model, which goes here. And hopefully you can get a goodness of fit of 1. But in either case, you minimize with respect to optimizing these parameters by least squares. How do we get these aspherical atomic electron densities? What we do is we break these up into atomic pieces using Hirschfeld's method. And these are 50% contours of these Hirschfeld atom electron densities and urea molecule. They're actually quite sharply changing on this surface at this 50% level. You Fourier transform those, and you see they're not spheres at all. And so there's a directional dependence there that coming from your wave function. So you get those structure factors and you can refine. Okay, that's called Hirschfeld atom refinement. There are other methods you can do. Our chairman has explored different kinds of atoms in a nice work by Michał Chodkiewicz, a very nice piece of work. It was a pity that the other atoms didn't seem to work any better than the Hirschfeld atoms. I had wanted to do that myself, but you know, I'm a bit slow. Okay, so now case 2, when we have more parameters than data. Now, typically, say you want to refine the molecular orbitals in your wave function. Now, there's usually a lot of molecular orbital parameters in your basis set, usually far more than data. So we need a different kind of method. And this is the reconstruction procedure, which I was talking about before. So we choose a wave function where the parameters are determined by minimizing the energy, as before. We do the experiment. And now, instead of minimizing the least squared, chi-squared, we minimize a weighted sum, a weighted average of the quantum mechanical energy, which was minimized here, or can be minimized, and the least squares error. So it's not just minimizing the least squares error, but a linear combination of two quantities which are being minimized. So let me write that like this. So here's your Lagrangian. Here's the energy, which is a quantum mechanical energy, and it's lambda. This is called the Lagrange multiplier. It's just a number times your least squares error. And you minimize that quantity for different values of lambda. Okay, let's have an explore for how this works. If we put lambda equal to 0 and we minimize and get the parameters, well, there's no least squares error. So we're going to recover a pure theoretical wave function, a pure calculation. Okay, we understand that. What if lambda is infinity? So if lambda is very, very large, and this is just 1, then the term here dominates the quantum mechanical energy if that lambda is very large. So this term makes no difference. So in the case when lambda is very large, we get some kind of least squares fit, but not really, because we have many more parameters than data. In fact, what we get is a regularized least squares fit. And in the intermediate region, we get some kind of perturbed wave function, one which has a lower chi-squared, which agrees better with the experimental data, but it has a higher energy, because the lowest energy you get is when you minimize without this term. That's the best wave function. So we take a hit. The energy goes up. It's not as good as it used to be, but on the other hand, your wave function agrees with the observed data better than you might expect. And this is what you see. As lambda gets bigger on this axis, you can see that the chi-squared starts to go down. And here on this axis, we plot the molecular energy, and it starts to go up as a function of lambda. Okay, so let me summarize. An infinite number of parameters in principle can be used in this method, which is crazy. And all you only need is one piece of data. So you can really tweak with your theoretical wave function and get some kind of reconstruction of what's happening, incorporating your experimental data. So this is not an experimental determination of the model parameters in the usual sense, where you pick a model, stay with your model, and you need to have at least 10 pieces of data for every parameter that you use according to a rule of thumb. It's not like that, because the experimental information and theory are mixed together in an uncontrolled way, right? So it's more like a learning or reconstruction procedure. I'll skip that last point there in the interest of time. Okay, so let's go now to some of the results that we were obtained, and we're really nearly out of time. Well, let me just try and keep going. Here's the original work from Daniel Brinwood, who now works for Defence Industries in South Australia. And you can see here the effect on the charge density of the Hartree-Fock wave function when we did this fitting procedure with lambda. And what you can see is, here's the oxalic acid moiety with 4 surrounding water molecules. We have a great buildup of charge on this hydrogen here, and some change on these around this oxygen here and this oxygen here. Now, it turns out in our most recent work, we are absolutely sure that this was due to a wrong bond length here. So initially I thought there was maybe some new physics, but no, it isn't true. In fact, if you use the Hirschfeld atom refinement method and then do, already at that stage, the structure factors are within, they're only half a sigma outside the experimental measured uncertainties. So the Hirschfeld atom method, even without fitting the wave function, just changing the ADPs and the positions, is nearly reproducing the experimental data. There's a little bit left to fit, and it does seem that the remaining effects are being fitted. So I'm coming now to the present, and I want to highlight a few important pieces of work very quickly. It's increasingly running out of time. So Giannoni's method here, what he did was, instead of using a single determinant wave function, he looked at these Kekulé structures here on the benzene molecule, and he used a multi-determinant spin-coupled valence bond wave function. So that's quite a tricky and impressive wave function, and rather than the single determinant wave function, he used this 5-determinant wave function and fitted that. And what he found was that the fitting parameters in front of these structures could be obtained. And you can see that structures A and B are the most important structures. So he actually, and perhaps that's expected, but these two structures are an equal mixture, as you would expect chemically, and these ones have less of an impact. Now, this is really interesting. We're getting now chemical information from the X-ray wave function constrained procedure. He didn't use, I don't think he used the Haar procedure beforehand, but I could be wrong with that. This is a wave function refinement using the lambda parameter to get the wave function indices. Amazing, absolutely amazing. This is probably something you know a lot about already, but the Haar procedure without wave function fitting, a few years ago, Magda visited and she did this paper which was supposed to take 2 weeks, but ended up taking a lot longer, because she did a massive amount of statistical analysis. But the end result was, for 81 molecules, hydrogen bond lengths could be obtained in statistical agreement with neutron diffraction measurements using data limited to 0.8 angstroms, which was quite impressive. Look, the error bars on those hydrogens were bigger than you could get from neutrons. That's perhaps as you expect, because neutrons diffract from the nuclei rather than the electrons, and the nuclei of the hydrogens is much better defined compared to their distribution compared to the electrons. Okay, here's an extension of that work, but essentially now trying, because these calculations are quite time consuming. So what's happening here is a procedure to use electron densities from fragments, like chemical groups devised also by Giannoni, onto these fragments, and using its complicated procedure. You need databases of fragment electron densities. You do the transfer, and you can do a kind of transferred wave function refinement. And that procedure also can get CH and NH bond lengths very, very well. And that procedure is the Haar extremely localized molecular orbital method with transfer from the database. Recently, well, maybe three years ago now, Justin Bergman visited, and we devised a similar fragmentation method based on Reader's capping scheme, and that also works very, very, very well. You can see that paper in IUCRJ. Unfortunately, hopefully in this year we'll be able to standardize this method. These fragmentation methods, I think, are going to form the basis of the new QCR procedures for molecule-based molecular crystals. Okay, so are neutrons needed? Yeah, maybe not. I mean, for big proteins, the X-ray data is not so good. Why restrict yourself anyway just to X-rays? You can combine neutrons and X-rays in this procedure. Here's a very exciting development from Florian Klimas, this Nosferatu program module in OLX2. It's getting really towards some kind of automation, and I think the OLX people are really working hard to make that available to you. I don't use that program myself very often, but I've seen people click and do things quite amazingly, which take me a long time to do. That's mainly because the OLX2 software is really very good at refinement. It has a whole lot of restraints and constraints and very nice things that you can do in there. And they have rewritten the Hirschfeld atom refinement module in there. So that's important. It's an interesting thing here is that Woinska and co-workers, Magda, have shown that the heavy atom hydrogen bond lengths use from this kind of a procedure a better model than the IAM model, but they're not as good as the light atom hydrogen bond lengths. Look, why am I interested in that? Because in biology you have heavy, like metal atoms, organometallic systems. Most of the interesting proteins are organometallics. Those are the things that do the catalysis. So, and what do they catalyze? They catalyze water molecules and hydrogen bonds. So you want to see hydrogen bonds right next to a very heavy atom, which is really very difficult to do. So they managed to get some information out here. Could have been better. I think additional restraints here with zero electric field forces will certainly nail this kind of problem. I hope so. And then we'll be in real business, especially when we have neutrons in play. Now, the time is 12:03. Officially, I have 2 minutes left. And I've just been blabbing away.
Dylan, please continue. Do not worry about time. Please continue.
Well, actually, I was preparing this talk and I still ran out of time on the future. So what do I think is the future? You asked me earlier today, do I think these quantum crystallography techniques will become a major advance in crystallography? I think they will for molecular crystals if there is the will to do it. It's really a lot of work. I mean, it was already a huge amount of work for Sheldrick to write his ShellX program. Indeed, all the other programs, Crystals or the old Xtal program, which is now defunct. These are hard programs that you write. Now we couple this together with quantum chemical techniques. It's getting quite difficult. I mean, the reason this could be done is really because of the ubiquity of the quantum chemistry wave function programs, which are quite robust, and multiple versions are available, and they generally work. Not as well as the structure refinement programs, but they generally work well. Not for heavy atoms, not for relativistic systems. Wave function methods don't work robustly, in my opinion, for periodic systems. We would love to have that working, but there's a lot of fiddling around. What you really want, experimentalists simply won't tolerate methods which require a huge amount of learning curve to them. So the software has to be very, very good. And in my experience, even writing for Crystal Explorer, trying to make that program, a relatively simple program, work robustly was a nightmare. So it's it requires, I think, the whole field to work together. And I think the developments are really coming on quite well. there's almost a kind of a race now to do things, which I think may be not so helpful. Maybe it is, I don't know. So I do think they will be standard based on DFT methods. Of course, as Peter Ewald said, why the IUCR was needed in the first place is standardization. We need some form of archiving of this information, because the information is really valuable. You don't have any more the atomic positions, but also the wave functions that go with them. Now, I just want to remind you, if you do a theoretical refinement of a molecular crystal, you don't get the correct unit cell within 5%. You don't get the precision within 10%, the bond lengths sometimes. So the information, the geometric information that can be obtained by refining wave functions against X-ray data is already very, very important. And we need to archive that. Once you have the wave functions, some of the archived information could be used to paint a huge variety of chemical properties. Look, it's almost an automatic procedure to calculate these chemical properties, thanks to the quantum chemists. Mr. Dirac said everything is known. And of course, that's what the quantum chemists wanted to do. They didn't want to have anything to do with the experiment, except insofar as to compare to the experiment and then laugh at the experimentalists and then go back to their calculations. And in this way, they have mainly killed the field of thermochemistry. No one really does any thermochemical measurements for small systems anymore. No way. For larger systems, it's problematic, especially when you have proteins and entropy effects. But yeah. So you can get things like refractive indices and NLO properties, things that we have done. Haven't gone back to that. Cohesive energies are already available from a program like Crystal Explorer, using very simple models, but they require wave functions. Now, if these wave functions are deposited with the structures, these things come out automatically, as do mechanical properties, even magnetizabilities and cross properties, NLO, cotton-Mouton effects, all these interesting kinds of things will come out. My personal interest is actually to improve the biological models. I think that's really very interesting, how all of these things work in biology. I was never interested in biology in the beginning because it's so complicated. But when I look at what goes on there, it's really, really messy. And I think if people just make an effort, something more can be done there. Okay, there's Peter Ewald. As I said before, QCR methods for inorganic systems. By the way, if we also have these wave functions, we can calculate not just hard physical properties, but qualitative properties too, things like bond indices and things like that. And there's various methods for doing those kinds of things. As I said, inorganic periodic systems may be harder to get quantum chemistry for, just because of the robustness of the programs which are required. And the other issue is the fact that the solid state physics community, when they model periodic systems for heavy atoms, normally use pseudo potentials, and that's code for removing the core electrons in your wave function. Now that's a real problem because the core electrons are some of the most important electrons for X-ray scattering. It's really not a sensible thing. And so that makes those periodic wave functions doubly questionable, unfortunately. But that still leaves a lot of things that can be done. One thing that I really want to just finish off on is this field of NMR crystallography, which is its own IUCR commission. In some senses, they are using quantum chemical programs to predict NMR parameters and use this to help them solve crystal structure. I think NMR crystallography is actually a subfield of quantum crystallography, in the same way that biochemistry is you can call it a subfield of chemistry, but it's so big, it is so rich that it really has to be its own field. And the same goes for NMR crystallography. So I really was a bit sad that I think we should approach these people to work with them, because that's really very interesting stuff there. Okay, so you can see where we're going with all of these properties derivable and available from databases like this. It's going to make it possible to model quite complex systems. I don't know how you would benchmark how correct these things are, but we are beginning. I'll just, I was going to mention something else. Managed to do some work on the 13 data sets that our chairman has produced on oxalic acid. And it was really interesting to see what we could get out of those systems. So that work is coming out soon. I hope you'll enjoy it when you see it. Okay, I had better stop. I've gone 2 minutes over the 70 minutes, and I really didn't expect to be blabbing continuously. I'm sorry about that. Okay, thank you.
Thank you very much for this excellent lecture, which is now open for questions and comments.
You can type your question in the chat or just raise a hand, and then we.
I got a thumbs up from people.
Yeah.
Oh, Simon is listening. Ah, Jean-Michel, I've been meaning to talk to you for a while. Okay, one day.
Maybe I have a question, Dylan.
Sure.
So you were focusing on wave function describing electron density, or using the wave function to describe electron density to compare it with experiment. But there are also nuclei, and they are also nuclei, and they are moving.
Yeah.
How about modeling the movement of nuclei? We
yes.
focus on that as well.
Yes. And recently, Bo Iverson raised that in Prague. That was a very interesting comment. And he said, yeah, we need to worry about the Debye-Waller factor in more detail. I think that's an important thing. It's something that really should be looked at. Now, I can say that one of the main problems with the Hirschfeld atom procedure is it takes the electron density in the unit cell and then breaks it up into atoms. That has no real basis in quantum mechanics. So that is not a valid thing to do. So you said, you know how I said that some of these things were, that's wrong. We shouldn't be making atoms into things and then convolving them with a nuclear motion. What should happen is something that I talked about at the CCAM meeting. It's a more advanced meeting. And what you require is actually 2 center ADPs, which I think you're getting at there. Now, I've always been really, really interested in those, and I have endless arguments with my colleague Hans Berge. He tells me, and I'm convinced, that in an atomic kind of model, you can't get the 2 center ADPs. However, if you have a wave function model, what happens is when the 2 atoms move together, the electron density actually changes. between the two atoms. So you can use this information. It's extra information. It's probably good information to deconvolve and get information about some of the two center ADPs. Which ones am I talking about? I'm talking about the ones between two atoms which are bonded. So we're talking about getting correlation information between nuclei. I think that's possible, yeah. Actually, I kind of figured out how to do it on holiday using, yeah, you can do it. There's a special issue for Hans Bayer coming out, and if I have time, I'll just write down those ideas. I think it's a really important thing to do. What kind of effect should it have? That's the question. Okay, so the bonding effect is pretty small, actually. Asphericity amounts to about, for light systems, first and second row atoms, amounts to about 10% of the signal at the most. And the bonding electron density is really rather small. You can comment the two center terms out, and it's about 1% to 2%. But that is for sure within the regime of measurable, high quality measurable information. So it should be seeable. Now, the other interesting thing is if you've got a heavy atom next to hydrogen, say you've got like I don't know, an iron or a tungsten or something with a hydrogen bonded to that, you've got a massive amount of charge density next to one electron. Now, what does a two center term do? It smears out the massive electron density onto the hydrogen two center term, and you get a massive correction there. You get a massive correction. So as regards the bond distance to the heavy atom, hydrogen distance to Magda did in the paper, I would expect that would have quite a strong effect, actually. Sorry to waffle on. All right, yeah, I did hear something from...
Yeah, there's a comment from Piero Macchi. If you have a metal close to hydrogen, probably the hydrogen atom has two electrons.
Yeah, but you know, 2 compared to 30 or 40 or something, that's the kind of thing you're getting more than a 1% change on that particular bond length is what I was kind of getting at. You know, next to what's iron? 26, isn't it? So that doesn't. Anyway, I think that's quite an important thing. Oh, and the other thing about the motion, of course, is anharmonicity. We had a 10-year. I remember talking about anharmonicity in 2013, and I had the results then. Still, the results haven't really changed for some of the systems. Hopefully, this year we'll really finish that anharmonicity work off. And I can tell you that we did some experiments reducing some of the high order data, artificially chopping that off, and the results were relatively robust for the so-called YQ28 system that Joanna studied when she first came out. Joanna Bonk, she was then. Now, Krzyszczakowska. Yes, there's a big change of a name there. Anyway, so far that work hasn't changed any of the results. What was stopping us there is there's this annoying symmetry problem that is happening, and we haven't really sorted that out. So it's annoying. Here's a question. Simon, you said, for example, for oxalic acid, the HAR plus theoretical wave function already describes the experiment very well. How much more useful, reproducible, physically meaningful can we get from the wave function fitting beyond HAR? Okay, well, this is my co-author, so he knows the answer. So in the point which I didn't cover in the paper in this talk, I believe we have a method which is fairly good for estimating the value of lambda that should be used in the XCW process. And using this method, which comes from DFT, and I thought we had made a mistake and it wasn't valid. My colleague Hans Bayer was really very upset about what we were doing, so much so that he is no longer on this paper and he's writing a paper against the paper that he was once on. So I'd be very interested to see his argument there. What the question is, how much more comes out of that? And the result was that the effect of the additional data using this method to estimate when to stop fitting is about 2 out of 40 electrons per cubic angstrom. So we can see effects, contour levels of the order of 1 or 2 in the valence region of these molecules. And there are really very, very significant differences in the core and some other places. So there's clearly some things which are very strange when we do the refinements on the oxalic acid with the 13 data sets of oxalic acid. Actually, if I have permission from Simon, I would like to send that paper to you, Christoph, because it is, after all, your data. And you can see if we have done anything strange there. More than likely, you'll get the paper to review anyway.
Looking forward.
Yes. So there are some vague effects that can be seen reproducing the theoretical. We fitted Hartree-Fock wave functions, and there's some vague correction towards the PBE and couple cluster type densities. Very, very vague. Like, you really have to work hard to see that. I don't know if we're imagining these things, but that they are consistent effects, which are complex and hard to do. I think it's important now to really improve on the experimental data collection. It's really becoming very, very critical, because the methods we're doing are already reproducing what's observed so well that there's hardly anything left to fit. And that's really a pity, because I think actually with these new detectors and with another careful round of data protocol analysis, we should be able to get at least another half order of magnitude out. It should be on these molecular systems. I think so. That would be really, really cool.
There's a comment from Hans Bet. The main problem with XCW is the fact that it models experimental noise to unknown degree. So that's...
Yes.
Yeah.
Okay, yeah.
So a method really to control the errors.
I would say it's so this is good that you're listening, Husband, because I kind of incorporated some of the responses that we were talking about as regards whether this is an experimental determination. It's not just the errors. It's modeling and changing the experimental structure factors as well as the errors, sigmas as well. And so just to speak to that. So the problem is that I haven't got the equations here. Could I share the screen perhaps?
Yes. On the left, the first, no. On the bottom,
Open.
there is next to the mic icon. You have a share screen of. Yeah.
It's all black. That didn't work. Okay, off, on. No, it's black. Let me try again.
Yeah.
Oh, run in app.
It may
I think
depend on your browser.
I think that this is a Chrome browser. No, they're both. Oh, window. Yes. Chrome tab. Aha, Chrome tab. Yeah, no, I don't want. Which one? This one. Share. Aha. What if I go like this? Oh.
Now we see the tab with the click
Now
meeting.
you see my screen?
Yes.
Okay, I actually don't see my screen. Okay, so here's the paper that I alluded to.
No, but we see just the tab of the meeting.
Okay, I can't show it to you. Okay, so getting back to the presentation. So, yes, in the constraint term for the XCW procedure, the lambda term contributes a very complex term which involves structure factors and errors. So, what Hans Bayet is saying there is he's saying that the errors are modeling experimental noise to an unknown degree. But yeah, that is correct. But you hope that the regularization is doing the best it can to correct any strange things from the data relative to the experiment, especially when you're using small values of lambda. If you're using very large values of lambda, then you're starting to introduce more experimental information into your model, and it's going away from your model. So I would say you're introducing you can think of it as introducing the worst of theory and the worst of experiment, or the best of theory and the best of experiment. So it's not the idea of experiment and theory as distinct items in this process is not necessarily the most sensible thing you can do. If you're worried about that kind of thing, it's really better to go not to use XCW at all, to nail down the effects with a proper model where there are not an unknown number of parameters in the model, like this wave function procedure, and sort the issues out there.
There's a comment by Piero that lambda equal number 1 is not something special because it does not have a universal meaning. It depends on the volume of the system.
Yes. Is that what Piero said?
Mm-hmm.
It depends on... Yes, that's right. So that is correct. And in this paper, which I couldn't show you, that the exact term which links the two includes the volume. What you can say is that the goodness of fit, or chi-squared term, is a kind of pseudo energy, which I think Piero is alluding to. And it would be possible to work out the exact term. It's actually 2 pi on V, where V is the unit cell volume. And if you actually weight the structure factors with 1 on k squared as well, then you can start to get terms which have actually the same units. So I hope I can publish the formulas for that. I won't be able to do the implementation. And then the lambda equals 1 point will be more sensible. I won't say it's completely sensible, but I accept his comment. It doesn't make sense. λambda1 is not something special, unless you take into account the volume.
There is another comment from Piero. Piero, maybe you want to tell it by yourself.
I'll read it out. Thanks for mentioning that I consider de Broglie's work as QCR. Let me just explain that while we use crystallography to prove how the electrons are distributed, he used crystallography, more precisely electron diffraction, to determine that electrons also have a wave nature, which is the core quantum mechanics. Yes, that was the essence of the comment in the paper, which is quite a nice read. Yeah, did I get that right? That you didn't really have a definition of quantum crystallography in there, but the purpose of the paper was sort of to say you basically nearly came out with it after Cyrillson's quote, and I sort of induced the definition from your paper. I don't know if that was...
I don't think it's so necessary that I give my own definition, but I think it's the one by Cyrillson was quite good in my understanding.
Except for the X-ray diffraction part.
Apart from being somewhat restricted on position space.
Correct.
And therefore on elastic X-ray diffraction only. But apart from that, I think it's nice. But I also wrote that actually definitions are not right or wrong, are just useful or useless, right? So
in fact, you wrote that immediately after that quote. So I mean, that's quite clear that the definitions are a little bit useless. I mean, look at...
Maybe another point is that you mentioned the nice paper by R3 about what you consider the beginning of quantum crystallography, but I think that 5 or 6 years before, Bragg published a paper where he reconstructed the electron shell distribution without having a wave function, but just the knowledge that there must be a shell structure in the atoms. I think that this was fantastic and honestly very brave, because we wouldn't be able to do that nowadays. I mean, he was trying to do that more than 100 years ago.
That sounds pretty interesting. So I presume, no, that wasn't the way that the radii were obtained. I think that was over.
No. That was extremely empirical, because it was basically doing a kind of Fourier transform of the very imprecise and inaccurate structure factors measured only to a resolution which is not adequate enough. Nevertheless, he was able to catch the part of the electron shell more or less at the right position with some shape which is not too far from. I mean, today we would not forgive such a loss of accuracy, but again, 100 years ago, this was extremely good. And again, this was done before having a proper wave function model for atoms. The only knowledge was that there must be shells. That was because basically it was everything still based on the Bohr model.
I think
before, of course,
from the point of view of combining quantum information, like genuine quantum information and data, that would then be regarded as quantum crystallography.
Yes, exactly. And that's the reason why I think that the Broglie work was also fundamental, because he explained us what are electrons. He told us that the wave mechanics is correct. Otherwise, all the hypotheses underneath will not hold. And this was
by the way,
done with crystallography.
I think it's right. Did you know this stuff from Ewald, which is basically saying a lot of what you were saying?
Yes,
you know I'm just reading Piero Macchi here. Of course, it's only in 4 paragraphs, but
There was also the introductory issue of Acta Crystallographica, which came probably just 2 or 3 years after that paper, where he also more or less wrote the same things, but trying to introduce the reason why we need a crystallographical journal. And he was making also the point, where are we now, where are we going, and so on. This was very very interesting and a little bit more advanced than the paper you mentioned.
Yeah. Okay. So that informed your thinking as well, I guess.
Yeah.
Look, he's a little bit down on Ewald on the importance of techniques, but I think what's special about the quantum crystallography technique involving wave functions with experiment is it's very hard to see how you could do better. I think in that sense, he's sort of saying it will be combined with this method or that other method and go down. I don't know, but it seems to me I can't immediately see how you could make a better model. It's almost like the end of models, this kind of thing. When you take your best possible model and you just squash it together with your best possible experiment, it seems there's no room left. So in that sense, I would disagree with Ewald's comment that these models will disappear. On the contrary, what will happen is with wave function based models, it becomes easier to model multiple experiments together if you can do it properly.
In this context, analysis of errors is important, and I would like to mention this approach by Julian Hen and his theory of systematic errors, and that's what we are missing in our treatment of data, in our treatment of experimental data. So that's would be great to see a kind of application of his ideas in the context of, say, refinement of experimental wave function, of lambda change, etc. So that's waiting for somebody to do.
My feeling is that this thermal motion thing needs to be sorted out quite urgently. Because it's a bit of an unknown. And another reason I want to sort out the thermal motion model with going back to essentially a 2-atom type approach is because the structure factors are so much more easy to calculate. So a lot of the problem with Hirschfeld atom refinement, apart from the wave function calculation, is the integration to obtain the aspherical form factors. In the original formulation, we used analytical formulas, and you get much more precise results and quicker. So there's a practical reason for doing it, and there's a scientific reason to investigate that. And if that all pans out, then I would go on to this. These two things can go simultaneously anyway, I think. But I think it's about 20 years ago, just to inform the younger people, I was sitting at the very start. There were really that was the time when CCDs were first coming out. And there was a thing called the taper, which is where the CCD had optical fibers connecting the fluorescent screen onto the detector. And that taper was a bit of an issue. And I don't know if that problem ever was fully dealt with, but people just gave up trying to think about it. And now we have these solid state detectors, and I think we can control these errors a lot more. And I think they should. I really think, apart from this thermal motion thing, the next stage is to go really back to the experiment again. So, and I'm sorry for using your oxalic massive data.
No,
but I think that
no, I'm
always wanted to do the beginning of the wave function project, and we were supposed to get everyone doing the same system. You've basically done it all yourself on different machines. As far as I'm concerned, that's it. That's the complete.
I'm very happy about this. Don't worry. These data are to be used useful for other researchers, scientists. So I'm very happy that you are using them. These data sets. Anyway, we have a comment from Joseph.
Oh, Koziszek. Okay. There are always inaccuracies in the experimental data. Some small systematic errors in the theory as well. Oh, definitely. And what about the chaos theory? Is wave function the solution? I don't. Well, for systematic errors on the theory side of the model, the energy part, we know that if we can improve the model, like to use spin couple VB or some other kind of, improved density functionals, maybe, fourth rung GGA type functionals, we know things are definitely getting better. So in that sense, you're doing better on the theory side. And then you wouldn't expect to use as much of the experiments. And you could then say that the experimental wave function, the wave function part of experimental wave function theory could be the solution in that circumstance. But, if you've got terrible systematic errors on your data, there's not really very much you can do except to fully analyze what they are. Hansbayer reckons that the background and thermal diffuse is a big issue, especially for the weaker reflections up high. So something could be done there to improve possible systematic errors there. Another thing that I suspect is quite important is extinction or multiple diffraction. So when you're on the eval sphere, if you have some quite strong reflections, there's going to be intensity stealing. Now that is something that we can do something about in the theory. We could do the second Born approximation fairly easily, I think. The problem with that is you would then have to fit to individual frame data because it's orientation dependent. So the experiment then would have to be done by doing exactly the same frame positions, not just collecting. Your data collection strategy would have to be different, I think. So at the moment, you're just covering the HKLs as many times as you can with different detector orientations, but what you would want in this case is actually identical orientation multiple times. Maybe
not necessarily, because this is what electron diffraction people are now doing. So you collect the data with fine slicing. So you go through the one reflections and you have it on several frames. And that's how.
Yeah, is that all right? Yeah. I guess if it's on several frames, it's the same eval sphere. So you're right. Yes, I take that back. But wait, what about the psi angle? Yeah. No, because you can have different psi angles, and then the different psi angles will bring different reflections onto the sphere, and then there will be different second order. So you need the same orientation. But maybe I'm misunderstanding what the electron diffraction people are doing. Actually. This fine slicing thing, I don't know.
Then they treat each reflection independently, right? It's not like they analyze the entire frame.
Oh.
Yeah, but
I mean,
it's how the dynamic refinement.
Oh, they're using dynamical. Yeah, I mean,
Yes,
yeah. Okay. So
works.
that's basically
Yeah.
what I'm saying.
Yeah.
Yeah. And I see what you mean. You mean the Moody, the Cowley-Moody fine slice technique for electron propagation through the crystal. Yeah. Okay, that's what you mean by slicing.
No. I mean that while you collect your diffraction data, you record a movie. How the reflections passes through the Ewald sphere, and you have so you have a profile of your reflection, not just.
Okay. Yeah. Okay. Yeah. I mean, in principle, then you can get, if you can deconvolute the dynamical effect, then you're going to do quite well. Yeah. Anything where you can get extra information with a variable parameter and modeling it, it's going to work quite well. By the way, coming back to Kolyushek's thing, another inaccuracy. I remember when we first met, when we came to Bratislava, you showed me the software which was modeling the shape of the crystal. Nowadays, of course, they use that blessing technique to sort of squash everything onto a sphere. You know, this multipole spherical model, so you don't have to model. The idea is you don't have to model the shape of the crystal. But I'm a little bit suspicious about that, to be honest. I think that's another systematic effect that could be dealt with.
Are there any more questions or comments? We can. Liliana is typing one. Let's wait for this. Let's wait for this question or comment. Well, that is expressing also my feeling. Dylan, really, thank you very much for this excellent lecture and very interesting discussion.